Hi folks, this is Mr. Ackerman here. Welcome to our video. This one deals with a review of position, velocity, and acceleration graphs, also called position time, velocity time, and acceleration time graphs, or maybe you know them as dt, vt, and at graphs. Now this is a review, so it's assuming you've already taken the grade 11 course and you've done the kinematics unit. I'm not going to go into too much detail on what we're about to cover. I'm going to assume that you did that in the grade 11 course. However, if you are in grade 11, you're more than welcome to watch this video. It might serve as a good review before a test or an exam. Anyway, what we're going to cover today is the following. First of all, when you look at a graph, you notice, among other things, its shape. So the question is, just by looking at the shape of the graph, what does that tell us about the motion that's being described? Also, once you get beyond shapes, you want to talk about numbers. So just reading a graph, how do we read them? And of course, as you probably learned in grade 11, when you have graphs, there are certain other calculations you can do, not just reading off a graph, but for example, calculating the slope or the area underneath or above a graph, and we're going to talk about what those mean. So we're going to look at each of the three graphs, the position, the velocity, and the acceleration graphs separately. So let's get started. I'm going to move on to our first slide here, position time graphs. And by the way, got to give credit where credit is due. All of the images you're going to see are taken from our book that we're following in the course, Physics 12 by Nelson. Okay, so the first graph that I'd like you to have a look at is this one over here. It's a position time graph. D vector is position. It has a magnitude in centimeters and a direction south. There should also be a reference point, but I think the book wants you to assume that the reference point is the origin, and the time is measured in hours. This graph over here is, as you notice, it's curved, whereas this one is straight lines, and that's why I wanted to include both of them. So first of all, as I said in the intro, we're going to look at things like where their shapes tell us. So let's go and just make a few notes about the actual shapes. For example, here you see straight lines, a straight line going down, a straight line going up. If you recall from grade 11, a straight line on a position time graph means that the velocity is constant. So we can summarize that here. Straight line means that the velocity is constant. If you have a curved line, like you have here, that means the velocity is changing. And as a side note, of course, if the velocity is changing, then that means there is acceleration. So we can also write that in. Okay. Now, a straight line that is sloped anything other than horizontally means that we're actually moving. So you can see the position is actually changing here. As time goes by from 0 to 1 to 2 to 3 hours and so on, the position changes from 50 centimeters down to maybe 25 to 0 at the origin, down to negative 25, down to negative 50. So here we have slope not equal to 0. That means we are moving. And of course, a slope equal to 0 would denote that we are stopped. There is no area on this graph where sorry, there goes my phone. There is no spot on this graph where the line is actually sloped horizontally. So you might argue, well, does this object that's being described, does it ever stop moving? And you might think, well, no, it doesn't stop moving. But let's make another observation here. We notice that the position's going from 50 down to 25, back to the origin, now passing the origin, going to the negative side, which by the way would be negative south, which would be north in this region of the graph. And getting back to that, so we're actually moving north here, and then all of a sudden we start going back to the origin, 25 away from the origin, at the origin, now 25 beyond the origin, 50 beyond the origin, and so on. So right here we see that there's a turnaround. And if you're going one way and then you turn around and start going the other way, and you're moving in a straight line one-dimensionally, this is a one-dimensional graph, of course, it's a south-north in terms of position. If you turn around, there must be a stop in there. So technically, this object does stop, although the pointiness of this graph here means that the slope isn't equal to 0. For those of you who have taken calculus, you'll know that the slope is undefined here. It's a sharp point. But of course, I'm probably getting a little bit ahead of myself. A graph where you see a slope that is equal to 0, for example, suppose we had something like the following. Suppose we had this, and then a horizontal line, and then that. This would indicate a stop here. So I hope I didn't go into too much extra detail there. I just wanted to make the point that this graph does have a turnaround, it does have a stop, but maybe not the kind of stop that you were thinking of. So I hope I haven't confused you too much, but what I've tried to do is to just sort of give an idea of what type of motion is being observed here. Let's take a look at this graph as an alternative. Here we have curves, so let's look at what's happening. This object starts at the origin, and it moves several meters over several seconds. For example, after about 1 second over here, it looks like it's about 10 or maybe more meters east of the origin. So it has moved. But then in the next second, up to 2 seconds, it's only gone an extra few meters. So what does that tell us? It tells us that you move a lot in the first second, and then a little bit in the second second. So we're actually slowing down here. We're changing speeds, changing velocities, and of course that's what we indicated in the very beginning. So our analysis is making sense. Now we are turning around the same way we had a turnaround over in the first graph. So that means there's going to be a stop somewhere in here. But now if you zoom in on this, if you guys want to move your eye really close to the screen, because we have a nice curve here, there's actually an area where the graph is fairly flat. You could imagine yourself climbing a hill out in the country, getting to the top, and there's a flat area where you can kind of rest and look out at the surrounding countryside. That's kind of what's going on here. So here we do have that flatness, albeit a curved sort of flatness, unlike a sharp sort of area like we had over there. Now we start coming back toward the origin, and in the first second that we come back toward the origin, we really only move maybe 3 or 4 or 5 meters, but then in the next second we move a lot of meters, maybe 10 meters, and then we're back at the origin. So here we're actually speeding up. So let's make a couple notes here. We'll do this in blue to help you see a little bit better. In this area here, we are slowing down. And in this area here, we're speeding up. And if you look at this, the slowing down is also indicated by the fact that the steepness is becoming less and less. We're leveling off. So in other words, the slopes are diminishing. And of course the reverse is true here. Here it's getting steeper and steeper. You can imagine that if you were a skier going down a hill, the top part would be nice and slow and easy, and here's the part where you'd go, oh crap, I wish I hadn't gone down this hill. It gets very steep. Speeding up, slopes increasing. Okay, just got that in there. Okay, so in other words, what this is telling us is that slopes are telling us something about speed or velocity, and in fact that is one of the other calculations that you can do on a position time graph. So if you remember in the beginning I promised you we would talk about other calculations you can do as opposed to just reading them. I've already shown you some examples of reading graphs by talking about the numbers in terms of time and position, but now I'm starting to talk about slopes. These are the other calculations that I mentioned in the beginning. So you could actually measure the slope of any of these lines, and before I do it on the curvy graph, which is a little trickier, I'm going to go back to the, the straight line graph. Let's go back here and let's talk a little bit about the slope. So you guys know, for example, that slope equals rise over run. That's one definition that you learned. You also learned in math class that it's y2 minus y1 over x2 minus x1. And so anytime you calculate a slope here, let's see what it is you're actually calculating. The y values are actually position values. We're not in math class with x and y like this. We're in physics class with d, position, and t, time. So you're doing really position 2 minus position 1. And of course the x2 minus x1, these are times. You're doing a t2 minus t1. In other words, you're doing what we call a change. Sorry, I'm just going to do a little erasing there. What you're doing when you make this calculation is you're doing a change or a delta in position divided by a delta, a change in time. And this you'll recognize is the definition of average velocity from your kinematic equations. This is a basic definition of v av. So it's true, when you calculate a slope, you're calculating an average velocity. I could calculate the slope of a straight line here using any 2 points. I'm going to try to pick some points that are easy to read off the graph. That one looks pretty easy. It passes right through some of the grid marks, and so does this one. So let's see, what is my rise here? I go from negative 50 up to about 25. That's a change of plus 75 meters in a time from 4 to 6. So that's in 2 hours. And by the way, I apologize, that shouldn't be meters, that should be centimeters. So let's go back here and write centimeters. And of course I was heading from the north to the south, so I'm actually heading south here. 75 over 2 is 37.5. So that's telling me that in here I've got a 37.5 centimeter per hour south velocity. And that's an average. All right? I'm going to write it over here so it doesn't spill over into the other graph's writing area. Okay? And this is the V average. Of course, there's a different V average through here, and I'll leave it to you guys to calculate that. Keep in mind this one's going to be a negative south or a positive north velocity when you calculate that. Okay? So moving along, let me just split up the two sides so that we don't get too confused here. Okay, going back to this graph here, you might say, okay, well that was a lot of fun, now I want to calculate a velocity in here. But stop for a moment and think to yourself what you're asking. You want to calculate a velocity, but you know that the velocity is changing. So there is no individual velocity. You could calculate an average velocity here. How do you calculate average velocities? Well, if you're asked for the average velocity between any two times, then draw the point on the graph that corresponds to those times, connect a straight line, and calculate its slope. For example, your teacher may ask you, find the average velocity between 2 and 6 seconds. So you go from 2, okay, here's the point up here, and 6, there's the point down there. The velocity changes throughout this interval as indicated by the curves. However, there is an average over any time interval. There's an average for everything. There's an average for your mark over the semester. There's an average for the stock market over 30 years. There's an average for population over so many years. How do you do this? Well, I'm going to pick a different color here so that we don't get too much confusion. Let's get a straight line going. You just draw a straight line from start to finish. There it is. And that, if you find its slope, you'll be getting the average between the 2 and the 6 second mark. But remember, my initial question was, what about the fact that it's changing? There's no individual velocity at any one, that's constant throughout the entire motion. So all we can talk about is averages over large time intervals or certain time intervals, or we can talk about, for example, instantaneous velocities at a given instant. So for example, suppose you are asked to find the velocity at the 7 second mark. That's right over here. Here's where the object is at 7 seconds. how do you find that velocity? Well, if you remember from grade 11, this time you got to draw a tangent line. And now it's not going to be easy for me to draw a tangent line here, but I'll do my best. How's that? That's decent, but I could do better. Let me try again. Okay, there's a not terrible tangent line. This tangent line touches the graph in one spot at the 7-second mark, and therefore it tells me what the curving is like, or the slope is like rather, at that moment. Now if I calculate the slope of this line by picking any 2 points on the line and doing rise over run, that'll give me what's called an instantaneous velocity, and that is coming from a tangent slope. So to recap, we could say that when you're on these kinds of graphs, average velocity, slope of line, joining 2 points. Another word for a line joining 2 points on a graph, by the way, is a secant line. So if you hear me use the word secant line, that's what I'm talking about. It's 2 points joined. Here we had a straight line, so that was easy. Here we had a curved line, but the secant is still straight. The graph was curved. The secant line is straight. It joins 2 points. That gets you an average. And of course, if you want the v instantaneous, then you're going to find the slope of a tangent line. Okay, and that's pretty much all we do on position time graphs. We either read them directly off the graph by reading numbers or looking at their shape, or we calculate slopes in order to find velocity. And now that takes us to our next slide, which is over here, velocity graphs. So once again, just to recap, what are we going to look at? What do the shapes tell us? How do we read them? And what other calculations can we do? So first of all, shape. Well, if you look at the shape here, first of all, let me just give you a little hint. We only do straight line velocity time graphs in grade 12. You're never going to see a curve, or you'll rarely see a curve. And that's because, if you remember, the straight lines that you see here show us that the velocity is changing. In fact, here the velocity is going from 0 to 5 to 10 to 15 meters per second in velocity over the span of about 4 seconds. That's a changing velocity. So right away we can say, hey, changing velocity, and that means we are accelerating. Acceleration. That's the definition of acceleration, changes in velocity. So what I was saying is you're always going to see straight lines here, or you'll almost always see straight lines. We don't really do curves on VT graphs in grade 12. We leave that for university, or possibly for calculus. Okay. What do I see up here? I see a steady velocity. The velocity is staying steady at 15 meters per second for, about, what's that, 3 seconds maybe. So the object's still moving, but at a steady velocity. Here it was speeding up. Now I see the velocity coming down from 15 to 10 to 5 to 0. So this is also a changing velocity, but decreasing. And what do I see here? Right at this point is actually a velocity equal to 0. That's a stop. And now what do I see in here? I see velocities of -5, -10, -15 meters per second. Those numbers are getting more and more. -5, -10, -15. You could imagine if this was a thermometer and the weatherman came on and said, temperature is -5 this morning, and then later in the day said, now it's -10, later in the day said it was -15, it would be getting colder and colder, more and more cold. Same idea with velocity here. The velocity is getting more and more, but negative. So we're not slowing down here. We're actually increasing our velocity, but in the negative direction. Because remember, negatives with vectors refer to direction. So if positive numbers like this are east, sorry, that's a pretty awful positive sign, plus sign. Okay. I think I'm banned from drawing plus signs. Oh, now I'm totally killing the graph. I apologize, guys. Let's draw a nice plus there. See if I can do this. There we go. Plus 10 means plus west, which means west, but negative west means east. Here we're increasing the velocity to the east, or if you prefer, negative west. So don't get confused and think that the velocity is decreasing here. It's actually increasing, just in the opposite direction. And of course, finally in this area, look at what's happening. Negative 15, negative 10, negative 5, 0. We're slowing down. And eventually we're going to come to a stop right here where the velocity is 0. So don't get confused by these graphs. All you got to do in order to read them is just think of what the numbers are and try to interpret them in your head. Okay? Now that takes care of point number 1. What do their shapes tell us and how do we read them? Now, what other calculations can we perform on them? Well, hopefully you remember from grade 11 that on a velocity time graph, the slope refers to the acceleration. Because if slope, like we said, is rise over run, or if you prefer y2 minus y1 over x2 minus x1, or since the y values are really velocities, so that's v2 minus v1, and since the x's are really times, t2 minus t1, you should recognize this v2 minus v1, that's delta v, t2 minus t1, that's delta v. Hey, this is the definition of average acceleration. So the slope is, in fact, the acceleration. Now, since I promised you we're going to have straight lines here, that means you're always going to have constant slopes. You're not going to have to worry about tangent lines to curved graphs like you did in the position example. So life is a little bit easier here when it comes to slopes. We already talked about measuring slopes, so I'm not going to take up extra time by talking about that. Pick 2 points along the straight line, calculate slope like you do in math class, and voila, there's your acceleration. Watch out, slopes can be positive like this, or they can be negative like that, and that would correspond to positive or positive west, or negative slopes, negative west, which would be east. So keep that in mind. Now there is one other thing that we can do in terms of other calculations on a velocity graph, and if you remember from grade 11, that involves calculating the area beneath a graph, in this case here, or above a graph, in this case. In fact, it's the area between the graph and the time axis that we're interested in. What does this tell us, the area between the graph and the time axis? Well, if you recall, it's actually the displacement during that interval. So for example, if I look at this triangular area here, I know that the formula for a triangle, let's call this, just so you'll note, actually, let's go like this. As an example, let's do the area BW between 8 and 12 seconds. What do we got? 1/2 base times height. That's a half. The base looks like it's about 4, and the units are actually in seconds. So it's 4 seconds across, and the height of this looks like it's about 15. But hold on, it's negative 15. Negatives matter here because we're dealing with vectors. Negative 15 meters per second west. So I'm going to write that in here, negative 15 meters per second west. And when I figure that out, what does that give me? A half of 4 is 2, times 15 is 30, and that's negative 30 meters. Seconds cancels with seconds, and I'm left with west. Or negative 30 is the same as positive 30 meters east. So does that make sense with how we analyze this graph in the first place? Remember, the object that's being described here was moving to the west, speeding up. Maintained a steady velocity moving west. Then slowed down, still moving west. Stopped. Then started speeding up, but to the east. Remember, we wrote that in here. So yeah, in fact, this object was moving east between 8 and 12 seconds. How far? 30 meters. And so now you know what you can do with velocity time graphs. You can calculate slopes to get acceleration, or you can calculate area in order to get displacement. All right, one final graph to talk about is the acceleration time graph. And the good news here is there's only one thing that or two things that I'm ever going to ask you to do on these. First off, talk about their shapes and read numbers off of them. And then I'll talk to you about the other calculation that can be performed. So getting back here, let's get started. Okay, first of all, what is this telling us? The acceleration measured in meters per second squared east, this object accelerated at a rate of 1 for about a second. And then its acceleration suddenly dropped to 0 for an entire second and a half. And then it experienced an acceleration in the negative direction, negative east, which would be westward acceleration for an extra second and a half. So let's write that in. Here we have eastward acceleration of 1 meter per second squared. And notice how that's a constant value. It's a steady 1 meter per second squared acceleration. Here, there's no acceleration, which, by the way, means our velocity is constant. If we're not accelerating, our velocity isn't changing, we have a constant acceleration. And then finally, in this last region here, we have a negative east or a west acceleration. And again, it is a constant acceleration shown by the fact that the line is flat, negative 0.5 meter per second squared. Okay, so there's an analysis of the shapes. This is what sort of object might be doing this? What might be happening? You might be in a car, for example, that experiences an acceleration at a steady rate, kind of like you at a traffic light. Light turns green, you step on the gas and you begin accelerating. But then you reach a certain speed where you're happy with, and then you just lay off the accelerator or you ease off a bit and you just move at a constant velocity. And now your acceleration goes in the opposite direction. This could mean, for example, that you're actually slowing down for a little while, but at a steady rate. So not that kind of jerky motion you get with some drivers who are a little nervous, but a steady acceleration. Okay? So now we've talked about reading the graph and looking at what the shapes mean. And so now we're going to talk about the calculations. There's no slope calculation that we're ever going to perform on these. The only one that we do is area. So what does the area represent? If you remember from grade 11, the area, once again, between the graph and the time axis represents not velocity, but the change in velocity. So for example, in here, from t equals 0 seconds to 1 second, the area, this is just a rectangle, so it's just length times width. Length of 1 units seconds, 1 second. The height or the width, however you want to call it, 1.0 meters per second squared east. Don't forget to include your direction and your units. Now notice, this seconds and one of those seconds cancel. What does that leave you with? 1 times 1 is 1 meters up here, and 1 of the seconds left there, meters per second east. Now, warning, this does not mean that the velocity was 1 meter per second. It means that in that second, the velocity changed by 1 meter per second east. I can't emphasize this enough, but students often mix that up. And I'll give you an example of what I'm talking about. If the initial velocity at t equals 0 seconds was, let's say, 5 meters per second east. This graph doesn't tell us that information, but suppose it was. Then 1 second later, t equals 1 second, the velocity would have become, well, you're going 5 meters per second east, and you have a change of 1 east. That would be 6 meters per second east. So this area is giving you the change. It's not giving you the actual velocity. Okay? And I think that pretty much sums up everything that you need to know. I went into a bit more detail than I had intended in the beginning, and that's fine because we're reviewing. But a lot of this stuff, I picked up the pace when we talked about velocity and then acceleration graphs, because I'm assuming that you remember your grade 11 stuff, or hopefully it'll quickly come back. If not, you can do some reading in the book. And at this point, that concludes our quick recap of the 3 different kinds of graphs: position, velocity, and acceleration time graphs, being able to interpret their shapes, being able to read numbers off of them to figure out what the object is experiencing, and then doing the other calculations such as slopes and areas. All right, thanks for tuning in, and I'll see you again next time. Bye now.